Okay, I think yeah, no one else is joining. We can start if you guys are okay.
Right, right. So we will start our recording now. Okay. Hi, hello everyone. I'm Shautik, and today I would be talking about reinforcement learning and the basics of reinforcement learning. So the idea of this session would be to give you a brief overview of reinforcement learning. Why is it important? And we will like to go through one example, worked out example. I have some live code examples that I wanted to show you about. So without further ado, let's begin. I want this session to be interactive as possible. So if you have any questions, feel free to interrupt me. I would like to uh, continue from then on. Okay, so let me just share my screen and then I think we can proceed. So let me know if the screen sharing is working. I think it is.
Yeah.
Right. So the topic would be about reinforcement learning. Reinforcement learning. So before proceeding with this, I would like to highlight one thing, which is the way we predominantly human beings learn. So one of the main methods that we often learn, suppose a child wants to learn how to ride a bicycle. Now, pardon my drawing. So you have a bicycle in front of you, and you don't know anything about the how to ride a bicycle. So it's a very stick figure-ish kind of bicycle. And so you first jump on the bicycle, and then you randomly provide some inputs with your limbs. So, for example, you want to uh, paddle somewhat, and based on what you do, this bicycle may end up falling down, right? And eventually, when you have sort of uh, some parent guiding you through the process, or some other person guiding you through the process, you learn from a process of trial and error, right? So the idea is that you first have some trials, and if there are some errors, you correct your course of actions, right? So the sort of feedback that you get comes in the form of some sparse signals. What do I mean by sparse, and what do I mean by signals? Let's just dissect a bit. So sparse implies that it's not continuous throughout the time. So in other words, I get the signals at some discrete intervals in time, right? And this signal or this feedback can be positive or negative. So let me give you an example, further example. So suppose you are studying for an exam, right? And you are you have your entire year's worth of coursework. So this is one semester's worth of coursework, and you have some minor exams in the middle of your semesters, and there is one major exam at the end of the semester, and these are some minors, right? Now, when you have you when you are preparing for this entire semester, you prepare your entire courses according to what the teachers gave you. You have some self studies and so on and so forth, right? But at the end of let's say minor one, you get, let's say, some marks. Let's say you get 90%, and for minor two you get at least, let's say, 85%, and so on and so forth, right? So You are not getting these signals every day that you study. You just get them at very sparse intervals in time. So after minor one, after minor two, and so on and so forth. Right? Now, the objective of a learner is to maximize the sum of these marks, not marks. Yeah, sorry. Right? So in effect, what you want to do is over the entire semester, you want to maximize the sum total of the marks that you get for the semester. And similarly, when you have some other uh, perspective in control theory, there you want to maximize some reward formulation. I'm deliberately not uh, providing arguments here, subject to some internal dynamics. In other words, I want to maximize some sort of reward. So this can be thought of as maximizing rewards subject to some internal way that the world works. So suppose you have the ability to control this world by your actions, right? So you can change the course of your future. So this is a very human way of understanding this situation. So for example, let's say you have your entire learning experience as a set of actions. So suppose at each time, each day, so let's say this is the course of the semester. Let's say the semester is 365 days. And for each day, day one, day two, and so on and so forth, let's say your aptitude of a subject is, let's say, this progress bar. So at day one, let's say you have this amount of progress in a subject. This subject can be, let's say, chemistry, right? And at the end of each day, you are filling this bucket up. So this, the level of knowledge that you have can be thought of as the state of your knowledge, right? Now, at the end of each day, the new state of your knowledge is some existing knowledge that you have at kth instant, and maybe some function of the current state x and the action that you take. So this action may be, let's say, studying one chapter or studying two chapters. So the action may be a discrete set of values. So it may be one chapter, two chapter, or three paragraphs, or so on and so forth, right? Now, the effect of knowledge depends on your present knowledge and the current number of chapters that you study. Now, we often know that this is not a deterministic way, right? Suppose you read two chapters, you may or may not end up increasing your knowledge. So there is a sense of disturbances that may arise. So this may be the number of reels that you watch, Instagram reels, right? So This is your current state of knowledge. This is the number of actions that you take, be it studying for the test or so on and so forth. And this W may be a destructive noise or disturbance that is coming to the picture. Right. Now, so in essence, what we have over here is some sort of this dynamics that we have. So xk plus 1 equals xk plus f of k plus, uh, f of xk, uk, which is the action, and wk. Right. Now, you notice that this is your internal dynamics, which I mentioned over here. Now, we need to figure out if the current state X and the current action U is good or not. Herein lies the sort of reward formulation. The thing that I mentioned before, which was of this sort of structure. So I want to maximize the marks that I get. So suppose if you imagine this xk to be really high value, let's say I have really good competency of chemistry and I have been studying daily for, let's say, 2 hours, right? So you can imagine that this reward that I get would be higher. But on the same hand, if I have, let's say, the competency of my original knowledge in chemistry was, let's say, this much, and I was studying for, let's say, 1 minute a day, and I was scrolling for Instagram through on the course. So my reward or the net marks that I get may be a little bit less. So this sort of phenomena uh, can be encoded in this sort of process. So in this scenario, you have two things that are playing. So one is an agent. This agent can be you, it can be a controller, it can be a machine learning algorithm, it can be a recommender system, and so on and so forth, right? And there is a notion of environment, right? So, for the case of this system that I mentioned, learning for an exam, the exam may be your system, exam may be your environment. For a controller, the plant. So, suppose you have a industrial process controller. The controller is the actions that you take, and the environment is the system plant. So, for example, a stirring machine or something, so on and so forth. And for an ML algorithm, this may be the data set. And for a recommendation system, the environment is you. So the recommendation system would be giving you choices of a few movies, and you would give it feedback whether you like the movie or not, right? So, for example, the agent sends a action to the environment, and the environment sends the current state to the agent. So this is the current state. This state is very loosely defined. You can define it based on your applications. This action is loosely defined. This can be defined based on your based on your situation. And there is another way of telling whether the current state and the current action is good or not, which is called as the reward. So if I zoom out a bit, you observe this sort of feedback loop that is coming into play, right? So this is called the agent environment interaction. And this is something called as the Markov decision process. Let me write the full form of it so that the readers may be able to identify. It's called Markov decision process, right? Okay, so let me give you a very simple toy example. So suppose, let's say I have a set of states, and oftentimes this is called a finite state machine. This has applications in FPGA designing, sorry, digital circuit designing. Let's say this has applications in uh, uh, the SIR modeling, which was the pandemic modeling. So susceptible, infectious, and recovered. So suppose I have a population model where I have some amount of population which is susceptible to a disease, some amount of population which is infectious, and some amount of population which is removed or recovered. So this is called susceptible, infected, and recovered. So back in COVID days, this was the talk of the town, right? How many people are susceptible to a disease? How many people were infected? And how many people were unfortunately dead? So, uh, suppose you have this sort of model where I have three states, which is S, I, and R, and there is possibility of jumping between the states, right? So let's say this is the model that we have. So let's say a person is susceptible, there is some probability that they become infected. And if the person is infected, there is some probability that the person recovers or perishes, right? And if the person is recovered, there is some amount of probability that they become susceptible to the disease again. Maybe the immune system is not that great of that person, and they become susceptible to the disease again, right? At each stage, there is some probability that the states would transition among themselves, and there is some controllability in this situation. So suppose I have a susceptible agent and I inject the virus that I have. I don't know why you would do that, but let's say there is a possibility of doing so. Then there is a higher chance that the person becomes infected, right? And if I have, let's say, a miracle cure of the disease, I can inject that in this scenario, and there is some probability that the person becomes recovered. So this sort of the chain is called Markov chains, right? Now let's dissect this word Markov, right? So suppose I have the entire history of this state that I had. So x0, x1, x2, so on and so forth up to xn, right? Now this can be your the state which I mentioned, right? This entire trajectory of the state, right, is called a state trajectory, right? So the Markov property is the property of this state trajectory that the expected value of the future state x, let's say n plus 1, given the entire trajectory, which is x0, x1 up to xn, this is nothing but the expected value of the future state xn plus 1 given the current state only. So if you have Markov property, you can forget about the history. So let me give you an example. You can forget about history. So let me give you an example. Suppose I have a cricket ball. This is the cricket ball, and you are taking this cricket ball in a aeroplane to the final destination. Let's say this is called the Wankhede Stadium. And in the fifth over, let's say a famous bowler who catches hold of this ball and lobs it towards the pitch, right? Now, if the this situation was not Markov, right? If this situation was not Markov, then the probability of this ball being hit by this batsman and the batsman scoring a six depend could would have depended upon the path that this aeroplane took. But as we know, this is not the case. The only thing that matters at this moment when the ball is being thrown to the batsman is the pace and the actions of the bowler and not the history behind it, right? So the real world is oftentimes Markov. And if there is not, this is not, then you would have to have some special circumstances that you can uh, design for. Now, so let's focus on the sort of Markov chains and let's write the situation again. Now, let's say we have the expected sum of rewards from k is equal to 0 to, let's say, capital N, subject to, so you are wanting to maximize this, subject to the dynamics that I mentioned, xk plus 1 equals uh, some function of current state x, some function of current state, current action u, and some function of the current disturbance. Now notice, due to Markov property, I am not including history here. That means I am not including x0, x1 up to xn minus 1. I am just including xk here, right? So this is the genesis of reinforcement learning. Now notice two things, right? First of all, this function may or may not be known, right? And the second, this reward may be sparse. As I mentioned earlier, I may not have this reward at every step of the K, right? I may have this reward at sparse intervals of time, or even at the end of this episode, right? So let's figure out how do we solve this situation? How to solve this, right? What condition do we make sure that? Yeah. So you have a question, right? Yeah, you can speak
Yeah,
up.
yeah. Sorry to sorry
No,
to
no,
interrupt.
it's okay.
Yeah. So just thinking about this part where Markov values are not expected to include history, right?
Yes,
It seems a bit counterintuitive, right? Like if you have an event or you have a state, you have some dependency on your older iterations, right? How does this actually
yes,
work?
yes. Right, right. So let me clarify it over here. Let's say you have the entire history of this ball, as I mentioned, right? So let's say at t there is some history associated with this ball coming to this baller hand of this baller
Mhm.
at this instant, right? So the past may have different versions of coming to the same point. But if you are at the
Mhm.
current point and the actions that you take afterwards are the same, then all of these trajectories would be the same after this point,
Uh-huh.
right? So the
Okay.
only thing that matters at this point is this current state S and the action and not the history. But the
Got it.
coming to this point may involve a bit of history, right? But once
Mhm.
you are
Mhm.
there, your past is forgotten, right?
Got it. Right. So
Right.
you're basically looking at, I mean, we are considering that point where this thing came into existence. When we know that this is what we wanted, we are just going to go ahead with it, right? We do not care
Right,
about how it
right,
came to that point.
right,
True.
right.
True.
That's the
Right.
Markov property. Otherwise, this situation would be really computationally intractable. There is
Yeah.
a special class of Markov decision processes which are called partially observed Markov decision processes, or POMDPs, right? And many real world examples where we don't have the access to the full state, right? Let's say this state is a really big list of values, right? But in real world scenarios, we may have access to only a few subset of these values. We may call it observations, observation at K, right? Now, if you look at the observation only, this this property of Markov may not hold.
Mhm.
The expectation here, so let's say this is up to, let's say, O of 0. This may not be equal to the expectation of the given OK minus 1. So the observation may not be Markov, but the full state X is Markov, right? So for partially observed processes, this Markov property may not hold, right? And then there are a few examples, there are a few techniques how we used to solve this, but that would be a bit beyond the scope of this tutorial right now.
Yeah. Yeah. Sure. Yeah.
Yeah,
Thanks for clarifying.
yeah. So, so we looked at this scenario where we have to maximize the sum of rewards subject to the dynamics, right? Now, there are a few methods in reinforcement learning, and specifically this sort of dynamic programming, uh, which we want to talk about. So let me introduce something called a dynamic programming. Now, the readers or the listeners uh, that are applying for jobs in, let's say, the big tech scenarios and so on and so forth. Uh, One kind of algorithms that are oftentimes asked in these sort of interviews is sort of dynamic programming. So it would be good to understand the basics of dynamic programming and how do we approach reinforcement learning problems from this scenario, right? Now, let's say you want to visit from Delhi to, let's say, uh, give me a place that is far away from here. Uh, let's say that this is in New York.
I was going to say Honolulu, but yeah, yeah, please fine.
Sure. Okay, Honolulu works. Honolulu works.
No, no, no.
Okay, it's in Hawaii, right? Yeah. Okay. Now, suppose there are there is no direct flight from Delhi to Honolulu, as far as I am aware. Let's say there are a bunch of layovers to choose from, right? So let's say there is a flight from New Delhi to JFK, New Delhi to Paris, CDG, Charles de Gaulle Airport, and let's say there is a flight to Oman, right? And all of these, JFK to Honolulu, Paris to Honolulu, and Oman to Honolulu, exist, right? Now, suppose this is the possibility space, right? And there is Delhi to JFK, Delhi to Paris, and Delhi to Oman, right? Now, one can imagine that there is this sort of Markov chain that is occurring over here, right? This is a Markov decision process. Uh, from where did you come to Delhi? We are not wondering right now. We only care up to from Delhi to Honolulu onwards, right? Now, we want to minimize, let's say, the cost of travel. This cost may be monetary, this may be time, this may be, let's say, fuel efficiency. This this may be, let's say, the number of bags you can check in, right? So based on all these costs, you can assign a reward for, let's say, the current airport that you are in, let's say Delhi, and you are taking an action which is the aircraft that you are trying to go to. So let's say this is Delhi to JFK. So you can assign costs for each of these legs of the journey, right? So let's say Delhi to JFK takes some amount of money. Let's say this is 1 lakh rupees, right? For Delhi to Paris, this may be, let's say, 70,000, and let's say Delhi to Oman is cheap at 50,000 rupees. Right? Now, these numbers are indicative. Don't quote me on these. But let's say from JFK to Honolulu, you are getting a good deal at 20,000 rupees. And Paris to Honolulu, let's say this is around 50,000 again. And Oman to Honolulu is a longer stretch. So this becomes around, let's say, uh, 80,000. Right? Okay. Now, let's look at this, the second leg of the journey, right? Now, the dynamic programming is actually a way to solve optimal problems, optimal control problems. So this has been the genesis of dynamic programming. So there was this famous person named Richard Bellman who was instrumental in developing this theory. And the approaches that we will take today stem from his research in 1950s, right? So the Bellman principle is a very simple principle, right? So the core idea is that if you have an action to take at the current instant, right, the optimal optimal cost. So let me be specific over here. Suppose at each instance you have, let's say, three options in front of you, and each of the options has a future value associated with it. Then the current value quote unquote value of this state is the extremum of the three. So let me be specific. Suppose I want to have the optimal cost of Delhi, right? So let me work backwards through it here. So in this scenario, let me just copy this diagram here. Let me just paste it here, right? And in this scenario, what is the effective cost from JFK? It would be nothing but 20,000, right? So if you are at JFK and looking forward, you are paying 20,000 to reach Honolulu. And if you are at, let's say, Paris and looking forward, your effective cost is 50,000. And if you are at Oman, uh, you are at 80,000. Now, the interesting part comes when you are in Delhi. Read Delhi, right? Now, the effective cost for this leg of the journey, which is the JFK leg, is nothing but the transportation cost from Delhi to JFK plus the value of JFK. Is this clear? Right? So you have to take the jump from Delhi to JFK, and then JFK onwards, you have this 20,000 cost, right? So effectively, this is Delhi to JFK was 1 lakh, right? So 1 lakh plus 20,000. This is one leg. The second leg is Delhi to Paris plus value of Paris, and the third leg is Delhi to Oman plus value of Oman, right? So value of Delhi to Paris was 70,000 plus value of Paris was 50,000. So let me write down these values. So it is nothing but uh, this equals 1.2 lakh, right? And this is also 1.2 lakhs. And Delhi to Oman plus V of Oman is 50 plus 80. This is 1.3 lakh, right? The value of Delhi is the minimum of all these three values, right? And here there is a tie between the JFK route and the Paris route. So the value of Delhi is 1.2 lakh, and this corresponds to either the JFK route or the Paris route. Now, if you notice here, this sort of uh, this sort of equation is really common over here. So the value of, let's say, the next state is the maximum. So a minimum in this case, because this is a cost minimization problem. But if we have a maximization problem over here, which was like this, we would have maximum over all possible actions that you can take, the current state xk, current action ak, plus the value at the, so let me, v of k plus 1, right? Does that make sense? So for each state that you are in, you evaluate this stage cost plus cost to go. stage cost plus cost to go, right? And whichever gives you the maximum value, you pick that action, right? So if you have, let's say, let me give you a more uh, bigger example, and I won't assign, let's say, nomenclature to this, but here is the scenario. So suppose this is the chain that we are working with, and let's say for each of these situations, I have uh, these connections, and let me assign edge weights to all of these, right? So, so this is, let's say, 5, 4, 3. These edge weights are arbitrary, so don't quote me on this. This is 7, and, and let me make this a bit sparse so that you can see things. Okay, so 2 disappeared, right? Sorry. Let's say we have an edge connection over here. Uh, and let's say this is 7, this is 2, and this is, let's say, 1, 4, 5. And let's say this is 2, 3, 4. All of these weights are arbitrary, right? So let's assign some nomenclature: A, B, C, D, E, F, G, H. Now the goal is to reach from A to H, right? A to H. This is my goal. Now, as you can see, what is the if I want to solve this optimization problem, this is a very hard problem to solve analytically, right? If I'm looking from left to right, this is a really hard problem. So what we can do is we can solve it from the goal to the starting position, or in other words, in this order, right? So what is the value of E from E to H? What is the value? This is nothing but what are the possible actions that I can take? There is only one. So the maximization doesn't make any sense here, right? So let me change the color for this one. What is the value of E? It is the stage cost plus the value of H, which is assumed to be 0. Because standing from H, what is the cost of going to H? That is 0, right? What is the value of F? This is an interactive question. So what is the value of F?
Yeah, only one root, the two.
That's 2, right? What is the value of G?
Three.
3, right?
And so we're still looking at minimization, right? It's still a cost minimized problem, right?
Let's work with maximization now.
Okay.
Okay. Uh, now, uh, now let's look at this layer, which is B onwards. So what is the value of B? So let's write max, and let's figure out the chains that are here, right? So let me just move it to the left so that this becomes a bit manageable, right? So what are the chains over here? So there is a chain from B to E, which costs 5, and we can add the value of E. There is another chain which is B to G, which costs 1 and the value of G, right? So let's substitute these values, which is nothing but max of 5 plus E, which is 6, and 1 plus VG is 4. So max of 4, 6 and 4 becomes 6. Now let's look at the C, value of C, which is, there are two chains. Uh, there are three chains. One from C to E, which is this. The stage cost is 6 plus V of E, comma. The stage cost of 2 plus V of F plus and stage cost of 4 plus V of G, right? So let's substitute these values. So 6 plus 1 is 7. 6 plus 1 is 7. Uh, 2 plus 2 is 4. And 4 plus VG is 7. So the max is 7, right? And for similarly for D, V of D, let me write down the chains here. These are 7 plus V of E and 5 plus V of G.
5 plus VLG.
Yeah, what is this? So 8 and 8. Yeah, this matches out to be 8. And the final one and the main one which we have, V of A, there are three chains. So 2 plus V of B, 3 plus V of C, and 4 plus V of D. So effectively, this is 6, 7, and 8, right? So effectively, we can see that this is 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. So the value of VA is 12, right? So it would take effectively the optimal cost from A to H is 12 for this maximization problem, right? And if one can imagine if we had minimization problem, we could pick the lower values over here and we could work out the max again. And there the situation would be around this would be 4 and 4, right? Both would be 4. So the optimal value there would be 6. What is the minimization problem? Right? You can do this as an exercise. Take any arbitrary Markov chain and pick these values as you like and solve the minimization problem. You would see that essentially this boils down to this equation, which I wrote down uh, earlier, which is maximization or minimization over the actions subject to the Rxk ak plus the value of xk plus 1, right? Is there any questions till now? This was a big uh, statement, right?
Yeah, just a question. Like for one scenario, like not just one, maybe two actually, right? There can be cases as you saw probably in the Delhi to Honolulu case, right? If you have
Yes,
two values which are competing for being the max, or maybe
yes,
in,
yes,
in the other
yes.
case as a min, then how do we kind of decide?
Based on the maximization problem, both are equally valid answers. But if you have some multi-objective optimization, the
Mhm.
ties may be broken based on some other factor that you have.
Okay. So we will have other conditions to I mean, as a tiebreaker, sort of, right?
Yes, yes. So the reward formulation is one of the most important aspects of reinforcement learning. If you have good reward formulations, you may have only one or two optimal solutions. But if you have
Hmm.
poor construction of reward formulation, you may have multiple ties, and the RL agent may not know which to choose. So the effective tie breaking strategy and the reward formulation is a must to have. Right. So So this is known as the Bellman equation. So pictorially, if you have the current state S state uh, xk, and you have let's say action 1, action 2, action 3, and the next state. So effectively, I'm looking at one particular node and the set of next nodes, right? So suppose you have this sort of scenario. So this is state xk, and these are xk plus 1, right? So this value function v is known as the state value function, right? And the Bellman equation corresponding to it is this one, right? Now, here lies the xk plus 1, right? So if we recall over here, uh, what is xk plus 1 is nothing but some function of xk, uk, or ak here, and some disturbance, right? Uh, Oftentimes, this is considered to be Gaussian, IID Gaussian, uh, independent, identically distributed Gaussian. Oftentimes, it is the case, but we may or may not know that, right? Now, if you were to know this value, this function, if you knew it, if this was known to you, right, you could easily look at this formulation, which I mentioned above, Vk is equal to maximum over all actions r r of xk uk plus value of this function of xk uk and wk. If you were able to know this function and the disturbance, it would be easier solving this equation, right? Now herein lies the challenge. We often don't know the dynamics. A, the dynamics, or B, the noise or disturbance, right? So this formulation over here is called a model based reinforcement learning, right? But when we don't know the dynamics or the noise, this becomes impossible, right? So herein lies a new formulation which is called the Q function. So let me introduce this Q function, and I will take a few questions and then we would proceed to the live code examples, right? So what is this Q function, right? So let me redraw this diagram, which I was drawing again and again. So let's say there are three states and there are three possible actions that I can take. right? So this is action 1, action 2, action 3. So this is x of k, x of k plus 1, k plus 1, k plus 1. This here that I have drawn a very deterministic arrow. So if you are at state xk and you take action a1, you would land here. But that may not be the case, right? Because of this noise term over here, right? So suppose you are thinking that you are at current state, let's say 5, and you apply, let's say, action 1, and you expect to land at state 6. But due to the noise, you may end up going to state 10, right? So there is a probability or non-zero probability that the state may transition to some other state depending on the noise, right? But at each state, uh, I had an associated value function, right? Which was the state value function. Now, there is another kind of value function which is called the state action value function, which is called the Q function, right? So the idea is, what is the maximum future reward, maximum sum of future reward subject to the current state S and the current action A. Now, pictorially, it looks like this. So instead of taking, let's say, the state and the corresponding value functions, you take the action value pair. So the state and the action. So this is state and action 1. This is state and action 2, state and action 3. And if you look at it, this is nothing but Q of S and A is nothing but the stage cost plus V of next state, right? Without the maximum term here. There is no maximum term, right? So if you look at here, the value function had a maximum over the action space, R plus Vk plus 1. But here, this is Q is equal to R plus Vk plus 1. There is no maximum over here. Now, why do we care about this, right? So let's write the Bellman equation corresponding to this, right? So I want to ensure that both these sides q, k, and in the right hand side also I have q, k plus 1, right? Now, how do I do that? So if I look at the state diagram again, after each next state S prime, so this is current state S, I can take multiple actions. So this is A1, A2, A3. And after each state prime, I can take another set of actions, A1 prime, A2 prime, A3 prime, A4 prime, and so on and so forth, right? Now, the value of this chain is the maximum of all these state value action pairs, right? So let me write this down. So the value of this current state S and the current action A is the stage cost, which is currently I'm sitting as S and A, plus for all these future states, I can take a maximum over the A prime, S prime, A prime. So look at what I have done here. I have taken the maximum from the outer region to the inner region, right? So if I write the two Bellman equations here, Vk is nothing but maximum over Ak of Rk plus Vk plus 1. And Qk is Rk plus maximum over A k plus 1 Q uh, S k plus 1 and A k plus 1. Now, this function and this function are the same. And notice the dynamics doesn't play a role here. Here, I have to figure out the maximum over the dynamics of the situation. But here, the dynamics is encoded into this Q function inherently, right? So the Q function helps us solve this, helps us develop model-free algorithms, right? Whereas in this V function, I had to have the knowledge of the model dynamics, right? So let me do an example, and then we can straight away go to the code and see how we can learn to balance a let's say cart pole system without having to know the system dynamics at all, right? So suppose I have a grid world. Suppose I have a number line, right? And there are, let's say, one, two, three, four, five states that I can be at. So this is, let's say this all of these are numbers from 0 to 4, right? So this is my state space. So the state space is the set of 0, 1, 2, 3, and 4. And the actions, let's say, are -1, 0, and 1, right? Now, so if I had this value of, let's say, the states, all of these values could be represented by a list of numbers. So suppose this state S at 0 had the value of, let's say, 5, 4, 3, 2, 1. Let's say this is the setting that I am working with, right? But for the Q function, you would have a table of values. So you would like to, sorry, you would have this sort of table. So here I would tabulate all the states 0, 1, 2, 3, 4. And here I would tabulate all the actions. So this would be -1, 0, and 1, right? Now, notice here, right? Suppose I give you these values, right? And I'm saying that I am at currently at state 2, right? So this is the corresponding value, right? What action would I pick? I don't give you any dynamics, right? I don't tell you whether at current state 2, if I apply, let's say, the action of -1, what would be the next state? I don't know that, right? But see how this Q table helps us understand about this situation without having to understand about this dynamics, right? So suppose I give you for each of these, uh, so I have drawn one more column additionally. I apologize for that. So, so for each state action, let me redraw this. So, so for each state action pair, so for each of these bricks, if I give you the Q function for each of these, so let's say this is 5, 4, 3, 2, 1, -1, 6, 7, 8, 9, 100, 5, 2, 5, 9, right? So suppose I am at current state 2, right? And given the values of these functions, can you tell me which action should I prefer? So herein lies the situation. So the Q of next state, the current state is the stage cost plus the maximum over the next state of this next state, right? Now suppose all these rewards are zero. Suppose all these rewards are zero. Now the best value to pick from here would be the maximum across this row. Am I right? So the best action to take from state 2 would be this action 1. But you had no information standing from this value function table. But you don't need that information if you were to work with this Q function, right? Is there any question till now? This is a bit of like hand wavy argument, but yeah,
Okay, I'm going to give a new question. Where are we getting these
yeah.
Q values from, though?
Uh, right, right. So initially, uh, you would initialize this entire table with zeros, right? So all these values would be zeros. Now let me play this game uh, with let me draw it again here, right? So this grid world over here has, let's say, actions that I can play here, right? So
Mhm.
uh, let's say there is a goal position over here, and the objective is to reach this goal, right? Let's say this goal position is outside this grid world, and there is a bus, I don't know, waiting for you to come to this bus, and it would take you to the grid world, right? Now, this cost maximization, or sorry, reward maximization or cost minimization problem may have its own set of reward formulations, right? So suppose this state 0, 1, 2, 3, 4, right? Suppose
Mhm.
from this 2 position, you can take an action -1, 0, or 1, right? If you have, let's say, this is the dynamics, right? So if you
Right.
have xk plus 1 equals just the current state xk plus this action uk plus some noise, right? So if I am sitting at 2 here, right? 2, and I apply this action 1, and this disturbance is, let's say, 100. I don't know. Then this
Okay. Yeah.
becomes 103. But this
Mm-hmm.
103 is in the part of this sort of uh, state space, right? So you can
Okay.
project it, or you can do a modulo operation with respect to 5, right? So 103 modulo 5 becomes 3. So the next state becomes 3, right? Now, sitting here and applying this action UK, you observe that this next state becomes 3. Now, based on 3, you have again 3 actions: -1, 0, and 1. And let's say these values take you to, I don't know, 2, uh, again 4, and this becomes 4, right? And these also have their associated chains, right? So what you do is you let this game play. So starting from an initial state, you take some actions and you observe these chains, right? And
Hmm.
at the end of this episode, you may either terminate or you may like exhaust your limit of playing, right? So this
Mhm.
is an episode end. So you may either reach this nirvana or you may get stuck uh, in this sort of
In the
endless loop
cycle,
of
yeah,
chains.
yeah.
Yeah,
And you might
endless
run
loop
out
of
of
chains.
retries.
Yes, you may either terminate or not, right? Now you have this sort of pairs x0, a0, x1, a1, and so on and so forth, right?
Mhm.
Till xn. So what you do is you observe this reward and you propagate backwards in time. And what you do is you fill up these tables. So you would have the final state. Let's say that state is 4. And correspondingly, you had observed that the reward is 500. So you would place a 500 at the value that you observed, right? And
Okay.
based on that, you fill up the table for the previous one, which would be the stage cost plus the value of the next state. And you solve this backwards in time, and each time you fill up entries in this table. Let's say this is 500 and so on and so forth, right? Eventually,
Mhm.
you would land up something like this, right? Now, once you figure out this table, it's very easy to compute the policies, right? You would maximize at each state, you would maximize across the action space, right? So that's the way you calculate this Q function. Uh, Let me show you a code uh, at a later stage where this
Yeah.
would become a bit clear, right? Okay. Now, I have omitted a big detail in this scenario. So initially, I mentioned that you maximize the sum of rewards, right? From k is equal to 0 to a very high value, right? Now, when you implement this in practice, right, what ends up happening that this value of n can be really high, right? As I mentioned, right, this chain can continue for a really long time, and eventually it may either terminate or it may not terminate, right? Now, suppose I have some reward which is either 1 or let's say it's a positive value, right? So it may be, let's say, 100 or 200 and so on and so forth, right? When you add these values up, the chances are that this sum may not be bounded, right? So in effect, if you have an unweighted sum of these rewards, this may eventually end up diverging. So a easiest example is to observe this sums of, let's say, ones. So if I have an infinite sum of ones, right, this is actually an it's not defined, right? So there are two possible ways to handle this situation. You can either have a discount factor, or you can take averages, right? Now there are big books written about both of these, right? So if you were to figure out like the genesis of these two, I would recommend the book by uh, wait, I forget the name. I'm sorry, it's Dynamic Programming. Programming by, give me 1 second, yeah. Let me find out the reference because I want the
Mhm.
readers to
Yeah, yeah,
be
sure,
able to. Yeah.
sure. So referring to like some book which is specifically for dynamic programming, right? It's not specific
Yes.
to like RNN or anything else, right?
No, no, no. It's by. It's a very famous book. Uh, okay, if I Bertsekas, yeah, Bertsekas.
Yeah, we can.
So there is one chapter on discount factor formulations and one chapter on average value formulations. The essential concept of both is you want to maximize some gamma times gamma to the power k times r, which is the discount factor. I would explain a bit here. And another one is this 1 by n summation over k is equal to 0 to n, and you take the reward. Right. So we will not be focusing on this one, because it's a bit beyond the scope of this video. But let's look at the discount factor formulation. What is this gamma? If I This gamma belongs to 0 to 1, right? Now, as I increase the value of gamma, you would observe that this gamma has this exponentially decaying sort of phenomena, right? As we increase the value of gamma, this becomes more and more flatter, and eventually, one as it approaches one, this becomes closer and closer to a horizontal line. And as the value of gamma decreases towards 0, this becomes more and more asymptotically approaches faster to origin or the 0, right? So as this value of gamma increases, you can see the effect of the nearby values is more prominent as gamma is lower, and the horizon of this situation increases as gamma increases, right? So you can imagine, if you are to minimize short term rewards or maximize short term rewards, irrespective of long term behaviors, you would pick a lower value of discount factor. But if you want to have your agent be looking at long term objective maximization, you would choose a higher discount factor. So, effectively, here's the trade off. So, suppose there is a student who is trying to optimize for short term scenarios, right? So they want to have pleasure in the short term. They would like play games on PS5. They would go out and play with other people, right? But they wouldn't study it because that is short in the short term a really bad thing to do for that sort of person, right? But in the long term, this strategy would be detrimental for the learning, right? But if the student had a long term view and would recognize that at the current present moment, it is better to be studying so that I can maximize the future earning potential that I have, right? So this is the myopic agent, and this is the far sighted agent, right? So this is the role of discount factor. Now, any questions up to here? So let me quickly move on to uh, uh, the problems with the tabular Q learning, and let's look at something called the deep Q networks. which is one of the more popular methods in the literature. And we would end our discussion there today, right? Now, as you noticed here in the previous tabular example, we had a table for all the possible values of state and all the possible values of actions, right? And you would have, let's say, tables for these, right? Now, what if the state space is not finite? If this is the case, right, I can't maintain an infinite table, right? So the table would be like sort of infinite in this row. There would be infinite rows of this table, right? But I can't do that. So what you end up doing is maintaining a neural network, neural network, wherein the input is the state and the output is the Q values for each of these actions, right? So if I have this Q function being a neural network, so I can input this state here and I can get a set of values for each of the actions that I have, right? And as you can guess it, the best action to pick would be the maximum of these, right? Now, how do I train this neural network? It's actually simple. And if you look at the this Bellman equation, you would get the answer instantly, right? The value of this Q function should satisfy this sort of Bellman equation, right? So if I take the Q function and place it over here, and I write the the Bellman equation, I observe that I need to do this sort of scenario, right? Now, if I were to have neural networks for both these, right, what I can do is I can take this right hand side and subtract the left hand side from this equation, right? Now, in the ideal case, this should be equal to 0, right? But since I don't know these Q functions, so initially there would be some error here, right? Now, if I take this right hand side with R plus max of A, Q minus Q, this I define as the Bellman error, right? And this Q function has some neural network parameters, right? Now, if I just formulate a loss function, which is the squared of this Bellman error, neural network people would immediately see where I'm going with this. You can minimize this loss with respect to your neural network parameters. And you can offload this to any neural network library that you have. So let's go to the code example and let's end our discussion there. So yeah, let me just go to the let me just share my screen here, right? Uh, can you see the screen? Right.
Yes.
So I have written this PyTorch example, and I would be showing you the code here. So let me just visualize this situation. So let me walk you through the code, and then I would run the code here. So as you can see over here, there is this function called, there is this class called QNetwork, right? So it has this associated state dimension, the action dimension, and the hidden layers, right? So I create this neural network in PyTorch, which is nothing but a linear layer, ReLU layer, and so on and so forth, up until the last layer, which has the output of the action dimension. Right? Let's look at the training loop that I have over here. So there are, for some reasons which I won't go into right now. If there are questions, I would definitely look into it. There are two Q networks which are trying to learn the same situation, same Q function, right? The the challenge with the present scenario, if you had seen the uh, uh, so let me just go through the training example, and then we can talk about it. So so uh, when you try to learn this DQN, you have an episode, and this environment is the OpenAI gymnasium environment. So you reset the environment, and you observe the initial state, right? And for each time instant, you take an action from the agent, and you observe the next state, reward, terminated, and truncated, which are the API example of this gym environment. And you take the step of this action for this environment. Then what you do is you store this transition, the state, action, reward, next state, and done to this experience buffer, which is over here. This is a deck of a capacity, and at each time instant, you are appending the state, action, reward, next state examples, right? And the code loss function, if I go to the loss function, right? So you have a current action, current Q value, and a target Q value. So what is target Q value? It is nothing but reward plus one minus done. So this done is a if it is one, then the episode is done. So this component would be zero. Otherwise, if it is not done, this becomes zero. Then this becomes R plus gamma times the next value of Q. This next value of Q is the target network, which is the Q function, the maximum over uh, the set of actions, right? And you define the loss function, and you perform this loss dot backward, which is the PyTorch uh, backward, the gradient descent optimization, right? So let's run uh, this code, and I would give this code to you so that the students may be able to run this. So let's run this code, and you would observe that there is this cart pole that you are trying to balance over here. So we don't know the dynamics of the inverted pendulum, but we would be able to learn how to control this. So give it some time, it would be able to start. Yes, this is the startup. So you can see initially there are a lot of like falling down movements, right? But you can see here it is trying to keep it upright, but yeah, there it goes. Right? So if you see, the reward here was 144, which was really high from the average 166, right? So there would be some stochasticity, but eventually this would trend upwards. So it would take some time to train, and I would encourage the viewers to play with this code. and vary the different hyperparameters and see how the training progresses. Right? So yeah, this was till now my presentation. So I'm stopping this right now. So it would take a long time to otherwise complete.
Hmm. So if someone has to, like, as you said, like if someone wants to try this out,
Yeah.
are there any dependencies? Like, is it just normal Python and the packages, or do we need something?
Yeah. So the dependencies, I would have the uh, uh, sort of requirements file. I would give it to you. They can
Okay.
download.
So it's only Python modules, right? And
Yeah, Python
no
modules. Yes.
specific requirement. Okay. Okay.
Yeah.
Cool, cool, cool. Great.
Yeah.
So yeah,
So
that was
any
a
any question?
that was a um, I
May
I think
Yeah.
it was a good session, right? It was great to kind of get an overview of how you model this, what kind of computations that, or what are the formulas basically. Like
Yeah.
from a programmer's perspective, we might be just looking at code, but it always helps to look at the foundations. Like, okay, how do you get to that?
Yes.
Um,
Yes.
yeah,
That
so
was
that was
my
great. Thanks.
Yeah.
Yeah, thanks, Shotrik. Thanks, Mehul. But yeah, maybe just a quick, maybe two or three questions, and then we
Sure.
can wrap it up. Uh,
Sure.
so if someone wants to learn about RNN or maybe just reinforcement learning in general, what books or resources would you suggest? Maybe you
Sure.
can add them later, and we can share it with the people.
Sure. Sure. I can do that.
Yeah.
Yeah. So
But do you have anything on top of your
yeah.
mind?
Yeah, so there are a few books and a few video lectures that I would recommend. So the books, one was the Bertsekas book, Dynamic Programming. That's a really, really good piece of text. So when I started learning this, it was a really
Hmm.
helpful book. So Dynamic Programming by Bertsekas, Dimitri
Hmm.
Bertsekas. Uh, the second book is the genesis of all reinforcement learning tutorials. It is called the book by Sutton and Bartow. I, I don't. It's easily available online. It's reinforcement learning by Sutton and Bartow. So I would
Okay.
like to give you that in the chat. I would
Yeah.
I would send it to you
Yeah.
later.
Sure. Sure.
And there are a few tutorials from YouTube, which is there was this Google DeepMind lecture series, both
Hmm.
2012 and recently 2019 as well. There are a few lectures by David Silver from
Okay.
DeepMind, right? So there is this YouTube series. What I covered here is a fraction of what is there to learn. I would request like the readers and the listeners of this uh, video to be
Sure.
to go there and like look at for
Sure.
yourself. RL is a really intuitive framework, so it's effectively like learning as we humans do. Right? We have a
Hmm.
carrot, we have a stick. It's a carrot and stick policy, right? When you do good in your exam, people often give you chocolate, and when you do bad in your exam, ideally they don't, but they often like beat you with sticks or something. Right? So it's a positive and negative reinforcement. This idea of reinforcements came from the operant conditioning of psychology, and eventually it trickled down to this optimal control, dynamic programming, and then subsequently reinforcement learning. Right? It has been used in this RLHF, which is this new way of training LLMs, large language
Hmm.
models, right, to be more aligned to what humans expect. So uh, we give it positive rewards when it is aligned to what we are trying to do, and we give
Right.
it negative rewards when it's steering away from it. So that's the RLHF. And yeah, that's the gist of what I had to cover. Yeah.
Cool. Cool. Thanks so much, Mehul and Pratik. Maybe we can do this again sometime. Uh, as a
Sure,
follow up, perhaps if you guys get time. I know you guys are busy, but yeah,
sure, sure,
cool.
sure. Yeah. Thank you, Shurabda. Thank you,
Thank you then.
Shubhodita.
Thank you. Bye
Bye bye. See you. See you. Take,
bye.
Yeah, thank you, Shotrik.
see you. Take care.
Bye bye.
Take care. Yeah,
Bye.
bye.
Well, thank you.